Hello, I'm Kenny Getzandanner, a flight dynamics lead at NASA Goddard Space Flight Center and a part-time PhD student at the University of Maryland, working with Dr. John Martin in the Machine Learning for Dynamical Systems Lab. In this presentation, I will introduce our application of reinforcement learning to spacecraft operations and planning, considering navigation and environment characterization. The motivation for this work lies in the fact that spacecraft operations are complex. Individuals who perform mission planning and operations must balance a number of objectives and constraints, including safety, science, and navigation, which are often intertwined and conflicted. Consider the example of a spacecraft operating in proximity to a small body. While the main objective may be to collect science data, operators must first characterize the uncertain environment and learn to accurately navigate in order to perform precise observations. Observation constraints may necessitate specific viewing geometries, which in turn may require maneuvers. And the data must ultimately be downlinked before exceeding the capacity of onboard data recorders. All of this must be done while keeping the spacecraft and instruments safe. Traditionally, this planning process is manually intensive and time-consuming. So the question becomes, how can we automate this decision-making process in order to reduce complexity and resource utilization and, eventually, enable fully autonomous operations? To answer this question, we apply reinforcement learning, or RL. RL is a widely used approach to autonomy in the spaceflight community and beyond. It offers a versatile mathematical framework for decision-making and is commonly applied to solve Markov decision processes, or MDPs. In this context, the agent is a spacecraft operating within a space environment, tasked with performing actions to achieve objectives which are quantified as numerical rewards. We utilize proximal policy optimization, or PPO, as a state-of-the-art model-free algorithm for optimizing MDPs. We use PPO to train two separate deep neural networks, a policy network that takes in the state information and produces an action, and a value network which approximates the expected cumulative reward and used to optimize the policy. Rather than starting with a high-fidelity scenario, we first examined a simplified problem to assess the viability of the proposed approach and gain insights and intuition. Consider a spacecraft in a planar 2D orbit about an arbitrary central body, in this case, the Earth. The state is comprised of the spacecraft's 2D position and velocity, as well as the central body's GM and rotation. The state and uncertainties are propagated using two-body problem dynamics in a UD factorized Kalman filter. At each time step, the spacecraft agent may choose a single action among the following: range to one of three ground stations on the central body, subject to visibility constraints, perform an impulsive maneuver in continuous 2D space, or do nothing. In other words, we formulated a covariance analysis and the PR2BP as an MDP. The reward is a function of the change in the formal GM uncertainty, such that the positive rewards correspond to decreasing uncertainty and improved knowledge. In this formulation, reward values are bounded between 0 and 1. A cumulative reward of 0 corresponds to no improvement in the GM uncertainty. A value of 1 means it is perfectly known. Having both discrete and continuous actions that are mutually exclusive introduces a parametric action space. To handle this, the policy network and action sampling are implemented as follows. The policy network takes in the current state vector and outputs logits, which are used to describe a categorical distribution for each of the n discrete action components. In this study, the last discrete component, d sub n, is the control action. The network also produces bias and scale parameters, which are converted to means and standard deviations that describe two independent normal distributions for the potential maneuvers, or delta v's. The discrete categorical and continuous normal distributions are randomly sampled during training. If the discrete control action is selected, the impulsive delta V sampled from the normal distributions are applied to the spacecraft and execution errors added to the covariance. If any other discrete action is selected, the delta V's are not applied. PPO also requires the logarithmic probability for each action, as well as total entropy of the joint distributions. Please see the paper for how we calculate those values for a parametric action space. Now we move on to the specific scenarios analyzed in this study. For more details on the implementation and training, please refer to the paper. The first case, case 1, only considers the tracking and do-nothing actions and is meant to serve as a simpler baseline. Then we add actuation in case 2, gradually increasing complexity. In both cases, we compare results to a simple heuristic that always selects the station corresponding to the highest elevation angle, thus maximizing visibility. We also include a policy where actions are chosen at random. Neither the heuristic nor the random policy includes actuation. The two main metrics used for comparison are the cumulative reward and station visibility or utilization, which we will define later on. Let's start with case 1. For training and evaluation, we start with 100 random orbits with sizes ranging from roughly 6,500 to 20,000 kilometers and a random initial rotation offset between 0 and 2 pi. The central body GM and rotation rate are held fixed, as well as the body fixed station locations. The random orbit configuration for the final policy evaluations and the heuristics is shown here. Before getting into the results, it is worth noting that the ground station measurements are subject to a 0-degree elevation angle constraint, shown here by the white and gray lines. The station geometry is such that, for radii under approximately 13,000 kilometers, there are regions where no stations are visible, shown in red. Returning to the results for case 1, here's the station visibility percentage for the trained policy compared to the heuristic and random policies. Intuitively, a policy is performing well if it is tracking to stations that are visible. This plot shows the percent of the 100 trajectory realizations that selected a tracking action corresponding to a station that satisfies the elevation constraint. The heuristic does not have 100% visibility due to the visibility gaps mentioned previously. For case 1, the trained policy in green compares favorably with the heuristic policy in yellow and significantly exceeds the random policy in blue. This plot shows the total accumulated reward, where higher values correspond to lower GM uncertainty for each of the 100 trajectories in blue, and the mean of those trajectories in yellow. As expected, the train policy matches the heuristic policy mean in green reasonably well, although there is still some room for improvement. It does far exceed the random policy mean, however. It is worth noting the relatively large variation in the cumulative rewards for the individual trajectories in blue, which is entirely driven by initial orbit conditions. Actuation should improve things, at least in theory. So let's add it in. Surprisingly, when we first added actuation to the action space, the policies tended to fall into an apparent local minima and chose to forego actuation in favor of purely tracking. There's still work to be done here, but as part of the effort to understand this behavior, we looked at the correlation between the orbit configuration and cumulative reward. Returning to the results from case 1, there is a clear correlation between the total cumulative reward and initial orbit semi-major axis. Smaller orbits tend to spend more time in the station gaps, and the reduced tracking negatively affects reward. Above about 13,000 kilometer radius, however, continuous tracking is possible. Beyond that, the spacecraft state becomes less sensitive to the GM, but that effect is less pronounced, at least up to the 20,000 kilometer maximum. For the next set of runs, we decided to focus on the lower SMA cases in green and set the maximum initial orbit radius to 10,000 kilometers. The plot on the left shows the initial orbit configuration without actuation. After training a new policy and running it on these initial states, we ended up with the final trajectories on the right. As we can clearly see, the policy prescribed maneuvers that raised SMA. More information on the maneuver statistics are provided in the paper. Looking at the visibility for case 2, we can see that the policy chooses to maneuver at the beginning of the simulation, resulting in a lower visibility percentage. However, the higher orbits enable improved visibility for the remainder of the run. There is still a slight dip in the visibility around step 80 or so, which roughly corresponds to one orbital period. Similarly, we can see an improvement in the mean cumulative reward for the train policy compared to the heuristic policy. We also see that there is much less variation in the initial reward, in the individual reward curves compared to the case without actuation. And if we compare initial SMA versus cumulative reward for cases with and without actuation, we can clearly see a significant reduction in correlation for the train policy with actuation. So we can conclude that the policy successfully leverages maneuvers to increase reward and improve results. In summary, we were able to develop an NDP environment that couples actuation and planning, developed and implemented a parametric action space formulation, and established heuristics, baselines, and a complete training pipeline. While there is still a significant amount of work to go before these methods can be applied to a realistic spacecraft operations scenario, these initial developments and findings further demonstrate the promise of RL for autonomous spacecraft operations and planning, specifically when considering navigation and characterization. Thank you for your attention.